Welcome back, grade 10s. We're busy with the basics of bonding. So we have had a look at the periodic table. We've had a look at lithium and sodium, and we have seen where they fit on the periodic table. So now let's look at this atomic structure and how the electrons really look. So if you look on my screen, you'll see that there's this weird picture, and this is what the orbitals actually look like. So we can see we've got an inner orbital around here. It's a circle. Can you see that there? It's a circle, or spherical, more likely, because we're talking about something which is 3D. There's another one here. This is a spherical orbital over there. And then we've got these very weird ones that stick out like that. Now, can you imagine trying to draw this every single time we have to represent the electron structure of an atom? Very difficult. So we have come up with a notation to help us. And you probably know that this very first orbital is called an s orbital. And the reason why it's called an s orbital is because of its shape. It's spherical. There's another s orbital over here. There we go. But this is the second s orbital. Okay, so that's the second s orbital. This is the first s orbital. These weird ones that poke out, I don't know what they'd look like, but they're really strange. They are called p orbitals, and they are linked. So we have, you can see these lines. So there's one along here. So that's linked there. This one is linked there, and there's one that's linked there. So there are actually two of them that make up one. And so we've got 3 p orbitals. Now, when we write this, we have a notation, and we say that we start with the bottom of our list, which is, or the lowest energy level, which is the s orbital, spherical orbital. It can take 2 electrons. Remember, 2 electrons in an orbital, no more. So the first one, the very bottom energy level orbital, S, because that's its shape, and we put a little 2 at the top. That tells us that there are 2 electrons in this bottom orbital. Then we move to the next one, which is in energy, which is the 2s orbital. Okay, 2, the next energy level, and S, because of its shape, it's spherical. How many can go in there? Only 2. Okay, then we move to the next shape orbital. This is also in the second energy level. It is second energy level. What shape are they? Well, they are p. Okay, that's the shape, this dumbbell shape, that's the word I was looking for, this figure of 8 shape. How many electrons can go into those? Well, 2 in each. So we could have an electron here, and an electron there, an electron here, 1 here, and 1 here, right? So there are 6 in total, and so we would write the number of electrons that we've got in those orbitals above the p. So you might be familiar with this notation, but it is a way of writing down the electron structure, where the electrons are fitting in around the nucleus without having to draw this very weird picture. Okay, I want to go back to our periodic table, and we've seen this group 1, and we've seen that the lithium and sodium, they've got 1 valence electron, and they will be very keen to give that valence electron away. Why? Because they want to become a noble gas. That's what they want to become. They want to look like that. And so they will be more stable if they give their 1 electron away. But now what about these elements on this side? So on the opposite side of the table, we're talking about the halogens, and oxygen is also there. We're going to have a look at those, and we're going to see what their structure looks like, their atomic structure. So here we have them here. Oxygen, let's just go back and check its number, its atomic number. Oxygen is 8, okay, and fluorine is 9. So let's just check it out. Now, that's a lot in there. Let's just have a look at that. Let's start from the beginning. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, there's 16 electrons there. Let's check this one out. I think it's exactly the same, except there's one extra, so that's going to be 17 electrons. That means we've got 17 protons over here, 17 protons, and we've got 16 protons over here. Okay, what does that mean? Let's just check. That means that we actually have sulfur, we don't have oxygen, and we have got chlorine, because that's the atomic number. So we've got 16 electrons, and we have got 17 electrons. So we've got sulfur, that's got 16 electrons, and we've got chlorine, which has got 17 electrons. Okay, what is this telling us? Let's have a look at this. If we look at the outer shell, we see that there is a number of electrons that are a couple of electrons that are unpaired. That means that they don't have a partner. So these ones over here all have partners, you can see that. And so here's one here. So here's one electron, which is sitting in the outer shell, the valence shell. And here is another one over here. It's sitting here. Let's just check. That should, yeah, okay. And let's have a look at this one here. The 17 electrons, that is chlorine. What about it? It has got, I'll put in the extra one here. So that is paired. You can see it's paired electron. And there's a single electron that's sitting on the outside. Now, if we look at their structure, so that picture that I showed you earlier, if we just go back, at this picture here, if we look at their structure, we'll see that they're not so keen on giving away their electron. They would rather take on an electron to make their outer shell complete and become more like a noble gas. So let's move back to there. So what will happen is, I'm going to change my pen so we can see. What will happen, we've got a single electron here, as I've said, and we've got a single electron here. This is sulfur. What is going to happen? Sulfur is going to take on an electron. It would rather take on an electron to share with this p orbital, and it would rather take on an electron to share with this p orbital. Okay? So it would rather take on the electron than give it away. That is really important in bonding because it means that they would rather take on electrons to fill the valency shell than to give electrons away to have a complete valency shell that's underneath the valence shell. This one, so we're talking about chlorine. Chlorine would do the same thing. It has got one space to take on an electron, so it would rather take on that electron than have to give away 1, 2, 3, 4, 5. So it's rather going to take on that electron than to give 5 electrons away. And so it is going to take on an electron to complete its valence shell. So the same with sulfur. If we look here, it's got 1, 2, 3, hold on, let me, 1, 2, 3, 4. 4 electrons in its valence shell. It would rather take on 2 than give 4 away. So if we look at our periodic table again, we see that in this group, so we've got group 17, we've got group 16, and the same applies for group 15, that these atoms of these pure elements would rather take on the electrons. It's easier in terms of energy to take on the electrons than to give them away to progress to this status of being a noble gas. That has quite a big implication in our bonding. So I'm going to speak about ionic bonding quickly. Ionic bonding is about a a joining of a metal and a non-metal. So the metal in this case is the one that wants to give the electron away. And that is what it does. It gives the electron away so that it is more stable. When it gives the electron away completely, it becomes less negative. And so it has a positive status. Okay? It gives one electron away, it becomes +1. We call that a cation. A cation is a positively charged ion. Positively charged ion. What about the non-metal? Here's the non-metal. And that non-metal is chlorine. We just had a look at it. The non-metal has got a space over here. Can you see this space? In its p orbital where it can take on one electron. It's going to take on one rather than giving the 5 electrons away. So it gains an electron, and if it gains the electron, it becomes no longer neutral, it becomes more negative. And so it becomes chlorine minus. It is an ion. We call it an ion. It is a negative ion, and we call that an anion. An anion. It is a negatively charged ion. Now, this positive ion and the negative ion have an electrostatic force between them. And a positive and a negative will attract one another, we know that, and they will form an electrostatic force between them of attraction. They will form an ionic bond. So an ionic bond is one of where a positive ion and a negative ion are formed, and that electrostatic attraction, that electrostatic force keep the ions together. When we do a Lewis notation, so drawing out all these atoms is very time consuming. We have something called a Lewis notation. So I'm going to represent the electrons in the valence shell using crosses and dots. So here we have sodium, and it has got 1 electron in its valence shell. I'm going to change my pen in a moment. Let's go for blue. And what is it added to? It's added to chlorine. Now, chlorine has got 5 electrons in its valence shell. So let's check this out. 1, 2. We need to include the s orbital here as well. So here, this is the p orbital. This is the s orbital. So that's the valence shell. We need to include that. So it actually has 5 plus 2. So that will be 7. So 1, 2, 3, 4, 5, 6, 7. What's going to happen? This electron is going to be transferred. It's a giving of electrons. What do we end up with? We end up with a sodium plus ion plus, and I'm just going to draw it under here, this chloride ion, dot, 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 cross. Okay, there we go. That is the Lewis notation. We represent what is happening. Our product is then going to be sodium chloride. They attract one another. There is electrostatic attraction, and that is the product of this ionic bonding. The last thing, this is what it looks like. A crystal lattice is made. So what about this ionic bonding? It is between a metal and a non-metal. There has to be a 1.7 difference in electronegativity. Now, electronegativity is the greediness of an atom to take extra electrons. There is a giving of an electron to form a cation. There is an accepting of an electron to form an anion. There is an electrostatic force of attraction, and a crystal lattice that looks like this when we draw it out is what results. Grade 10s, join me in the next lesson. We're going to finish up with covalent bonding and metallic bonding, and we will do some questions. We will see you then.